गुड मॉर्निंग स्टूडेंट्स, वेलकम बैक टू आवर चैनल ऑफलाइन इंस्टीट्यूट। सो माय नेम इज़ करीना और आज की इस क्लास में हम बात करने वाले हैं बहुत ही ज़्यादा इंटरेस्टिंग टॉपिक के बारे में। तो जो टॉपिक है हमारा वो है क्वांटम कंप्यूटिंग वर्सेस क्लासिक कंप्यूटिंग। तो इस क्लास में मैं आपको एक्सप्लेन करूँगी क्वांटम कंप्यूटिंग और क्लासिक कंप्यूटिंग, इन दोनों कंप्यूटिंग में क्या डिफरेंस होता है। So in this presentation aims to demystify the complex world of quantum and classical computing. We will explore the fundamental principles that govern each paradigm, understand their unique strengths and limitations, and peek into the future to see how these powerful technologies will shape your world. Join us as we compare and contrast these two distinct approaches to computation. So classical computing की बात करते हैं, which is the foundation. बिट्स, इसमें 0 और 1 यूज होते हैं एज अ बिट, द फंडामेंटल यूनिट ऑफ इंफॉर्मेशन रिप्रेजेंटेड बाय बाइनरी स्टेट 0 एंड 1। लॉजिक गेट इलेक्ट्रॉनिक सर्किट्स होते हैं जैसे एंड और नॉट ऑपरेशंस। मूर्स लॉ, ट्रांजिस्टर डेंसिटी डबल्स अप्रॉक्सीमेटली एवरी 2 ईयर। वॉन न्यूमैन आर्किटेक्चर सेपरेटिंग मेमोरी फ्रॉम प्रोसेसिंग यूनिट। सो क्लासिकल कंप्यूटर ऑपरेट्स ऑन बिट्स which are physically system that can be in one of two states like 0 and 1. These bits are manipulated by logic gates forming the basis of all classical computations. The rapid advancements predicted by Moore's law has driven incredible progress, enabling increasingly powerful devices, and the von Neumann architecture with its distinct memory and processing components has been the dominant design for decades, foundational to today's computing landscape. Limitations of classical computing. Moore's law slowly. Physical limits are being reached for transistor miniaturization, inefficient for complex problems, struggles with large-scale factorization or molecular simulation. एनर्जी कंज्यूम करता है। डेटा सेंटर्स डिमांड एवर इंक्रीजिंग अमाउंट्स ऑफ पावर, डेटा वॉल्यूम। इट चैलेंजेस इन प्रोसेसिंग एंड मैनेजिंग मैसिव डेटा सेट्स. So while classical computing has propelled us forward, it faces inherent limitations. The physical boundaries of Moore's law mean transistor cannot shrink indefinitely, impacting future performance gains for certain complex problems such as quantum mechanical simultaneous simulations or large-scale optimization. Classical computers become prohibitively slow. Furthermore, the sheer energy consumption of modern data centers and the explosion of big data present significant environmental and processing challenges that classical architectures struggle to address efficiently. Quantum computing, which is a new paradigm. So, Qubits leverage superposition and entanglement for vastly richer information representation. Superposition. A qubit can exist 0, 1 or both simultaneously, allowing parallel computation. Quantum gates. Operation on qubits that exploit quantum phenomena like superposition and interference. Entanglement. Qubits become correlated where the state of one instantly influences another, regardless of distance. So quantum computing introduces a revolutionary approach, moving beyond binary bits or quantum bits or qubits. Qubits utilize two peculiar quantum phenomena for superposition, where a qubit can exist in multiple states at once, and entanglement, where qubits become intrinsically linked, sharing the same fate even when physically separated. So these properties enable quantum computers to perform computations in ways impossible for classical machines, opening doors to solving previously intractable problems. So now what is the difference between classic computing and quantum computing? So in this we use bits 0 or 1, qubits, superposition and entanglement. Deterministic results, in this we have probabilistic results. Redundancy for error correction, it is complex quantum error codes. Traditional algorithm, fundamentally new algorithms. Excellent for everyday tasks, exponential advantage for specific problems. Quantum supremacy, what it means? 2019's Google Sync mode claimed quantum supremacy with a 53-qubit processor and 10kx speed difference. Psychomode performed a task in minutes that would take classical system 10,000 years. 50x IBM's reviewed it. Challenged Google's claim, stating classical algorithms could complete the task in 2.5 days, 50x faster than Google's estimate for classical. Applications of quantum computing: drug discovery, material science, financial modeling, and cryptography. 4 applications. This is for simulating molecular interactions to accelerate new drug development. This is for designing novel materials with custom properties at the atomic level. This is for optimizing complex portfolios and enhancing fraud detection capabilities. And this is for breaking current encryption standards and deploying quantum resistant security. Current status, future outlook. Early stages: error correction, hybrid approaches, and market projections. Quantum computers are still in their infancy with limited qubits. Error correction is a significant hurdle due to qubit decoherence and sensitivity. Combining classical preprocessing with quantum for specific tasks is estimated to reach $86 billion by 2040, which is growing at 30% annually. Coexistence and collaboration, augmenting not replacing. Quantum computing will complement classical systems for specialized tasks. Classical's core role remains essential for structured logic and everyday computational needs. In quantum niche, revolutionizing specific industries with its power to solve complex problems. So in conclusion, we can say that quantum computing is not poised to replace classical computing entirely, but rather to augment it. तो आज की क्लास में इतना ही, मिलते हैं इसी तरह के नेक्स्ट टॉपिक्स में इंटरेस्टिंग टॉपिक्स के साथ. थैंक यू सो मच.